A useful auxiliary method to use with rotating disc electrodes is what they call the rotating ring disc electrode. The idea here is to have the same rotating disc electrode as we had before, but add on to it a second electrode that's in the shape of a ring concentrically arranged around it. So you have your central disc, and then arranged around it, I'm not drawing it very smoothly, but this is a second disc that would be a really bad electrode, but so the idea here is we would have three radiuses, one R1, R2, and R3, which is to the edge of the second of the ring. So this is the inner surface, and this would be to the R3 would be to the outer ring. And the idea with the rotating disc electrode is that it gives us additional information, quite a bit of additional information. The problem with one of the problems with the rotating disc electrode is that, remember, once we do that reaction on the disc, that material is gone. It goes out and is not seen again. So unlike in cyclic voltammetry, where we did a sweep and we saw the first wave and then we swept back, and that reverse peak is what we made on the forward sweep. We don't have that kind of information with the rotating disc electrode. We only see the first process. We never see what we made directly with the rotating disc electrode. The idea with the rotating ring disc electrode is that because that material is being swept out from the disc, we can use that ring as a way to analyze the products of the disc. And by adjusting the disc and ring potentials appropriately, we can get quite a bit more information. So the rotating ring disc electrode is kind of like the analog of a cyclic voltammetry experiment. Rotating disc electrode is like a linear sweep voltammogram. The ring disc electrode is like a cyclic voltammetry. Or if you like, it's like a double potential step or a potential reversal step in chronoamperometry, whereas the rotating disc electrode would be a single step chronoamperometry. Now the ring has, whatever the ring is doing, since we're rotating, it has no effect on the disc. So the ring is, as far as the disc is concerned, the ring is not there. But as far as the ring is concerned, the disc is driving a lot of what happens on the ring. First of all, we can imagine a couple of situations. Suppose that the disc is set to have no electrolysis. Well, if we're rotating this system, and if we look at a cross-sectional view, we have a disc, and if the disc is doing nothing, we just get a current that's proportional to the rotation rate and so on. But what we can do is, for example, have the disc making electrolysis at the disc. So now all the material that gets to the ring has always been pre-electrolyzed. So that will basically, you could shut off the ring current or modulate the ring current by changing the potential of the disc. And let's explore that idea a little bit. First of all, let me tell you something about the equipment you need with the rotating disc electrode. We need a bipotentiostat. It's not absolutely necessary, but to use the rotating ring disc electrode, also often called the RRDE, rotating ring disc electrode, RRDE, we need a bipotentiostat. A bipotentiostat acts like a regular potentiostat, except that its job is to control the potential of two electrodes simultaneously. And we haven't talked about potentiostats from an electronic standpoint yet. And I think what we'll do at the end of the semester is we'll spend a little bit of time talking about some of the equipment we need to use. But a bipotentiostat well, let's just leave it at that, can independently control the potential of the ring and the working electrode and maintain them at a desired value. Also usually allows to sweep the potential of the ring or sweep the potential of the disc while maintaining the other potential constant. And in some cases you could sweep both simultaneously, sweep them in opposite directions. It doesn't really matter. Usually a bipotentiostat lets you do all those sorts of things. So the idea is that we always have the ability to control independently the potentials of those two electrodes. The classic experiment is what they call the collection experiment. The idea here is that we have species ox plus an electrons to red. We can set the disk at a potential, let's call it E2, and if we look at our curve, E2 will set out here on the plateau. E1 would be here, and of course this would be our limiting current. So let's set the disk at E2, the ring at E1. So if we look at the electrochemistry going on, we have ox coming in to red, and at the disk, the red goes back to ox again. So what we're doing is we're making a reduced species transiently. As that reduced species sweeps past the ring, because we were setting the ring at E1, that's a potential at which we can reoxidize the reduced molecule. So we'll get a current that's anodic current by setting the potential there. And what we get out of this is a parameter they call the collection efficiency. And you can actually theoretically derive what that value should be, and you can also measure it experimentally, which is what's usually done. But given a particular geometry, and that would depend, of course, on the ring thickness, the ring disk separation, the and so on, you can theoretically derive one. Typically, we're in the range of 50 to 60%. Sometimes a little bit better, sometimes a little bit worse. That value should be stable for reversible, not necessarily reversible, but for chemically stable oxidants and reductants. So as long as there's no chemical process accompanying these electron transfers, we should be able to maintain a stable collection efficiency no matter what the rotation rate is. As long as we're sitting, for example, on the plateau and of the reduction process and essentially the plateau of the oxidation process. So if N does change, the collection efficiency N does change, that would be indicating a chemical reaction, and that would be a good way to check that simply in a very static experiment. We don't have to change the potentials. All we do is change the rotation rate, measure just that simple ratio, and get our information. So that would be a good diagnostic tool. Okay. The other thing we can measure are what they call transit times. The idea would be we have making the reduced molecule at the, say, the edge of the disk as it swept along here. Now at the edge of the other disk we can go back to ox. And so we can measure those transit times, and that would be something we could determine theoretically. Now, how would that be affected by chemical reactions? Well, you can see that if we have a chemical reaction, as we minimize the transit time, the chemical reaction, depending on how fast it is, may or may not allow a significant amount of red to be undergoing a chemical reaction. So if the reaction is quite slow and or have a very rapid rotation rate, this can get across the gap rapidly and undergo the reoxidation before the chemical reaction can occur. On the other hand, if the chemical reaction is quite fast, then the reaction may be nearly complete by the time we get to the edge, and then we would get very low collection efficiency in that case. Usually the chemical reaction is fixed, and the rotation rates change. The idea is the same. As we change the rotation rate, the collection efficiency would change, and as we monitor the collection efficiency as a function of rotation rate, we can make a measure of the transit time and a measure of the chemical reaction rate if one is present. The typical way to plot these sorts of data, not in a static way, but suppose we do a little bit different experiment. First of all, we'll just get the limiting current for the current. Of course, that's equal to 0 there. And what we'll usually do is plot the current as a function of the disk potential. And if we hold the disk potential, or as we sweep the disk potential here, we can hold the ring potential at various values. First of all, we can have a system where we have plot I sub d versus E sub d, and that's what we have here. So we have the diffusion current. And we can sweep E sub d, and we can sweep it, say, from E1 to E2. And we'd get a normal looking wave, like a steady state wave. If we set, and then we plot IR versus E sub d, and we hold the ring at E1, then we'll get a curve like this for I sub r, the ring current. In other words, we're sweeping the disk here and measuring this potential. All the time we're sweeping the disk potential, we're holding the ring potential here. So as soon as something is oxidized or reduced at the disk, it's swept to the ring and undergoes an oxidation. And then because the potential is here. So we'll see a current for that happening as soon as we see a current for the other process occurring. So by looking at this, these two limiting currents gives us collection efficiencies. And so I sub r should in principle be equal to the theoretical the collection efficiency times the disk current. So how are we doing here? Okay, well, why don't we stop here for a brief break. Okay, all right, we were just talking about the rotating disk electrode and rotating ring disk electrode.